There are events that are already written, those of an unheard of beauty and unparalleled violence, which, in the near future, will unleash in the sky. Today we will discuss topics that are part of it. Funny thing, if we could go back far enough in time, we would eventually come across humans, whether they are your ancestors or mine, who witnessed the phenomenon we are going to talk about now. In the year 1006, a star of unparalleled brightness suddenly appeared in the sky, 100 times brighter than Venus. It cast sharp shadows on Earth at night, and at its peak was even visible in broad daylight. Then its brightness gradually declined, and after 2 years, it had completely disappeared. Astronomers thought they witnessed a star's birth. In reality, it was its death, the swan song. This is not fiction, it has already happened and it will happen again. Because there are in the cosmos giant stars or unstable pairs of stars that inevitably end their lives in cataclysmic explosions known as supernovas, and emitting in a few days as much energy as billions of suns combined. Over the last millennium, the appearance of these powerful ephemeral stars can be counted on one hand. We observed one in the year 1006 in 1054, in 1572 and in 1604. And each time when we point our telescopes, where these stars have momentarily appeared, we can see the remnants of vanished stars. The burning and expanding remnants are still visible several centuries after the explosion. On a cosmic scale, supernovas are rare, with an estimated average of 2 to 3 explosions per century in our galaxy. Space is vast, and most of the time these space monsters are for us only a powerful and new ephemeral light which, for a few weeks, comes to illuminate a distant constellation before disappearing. All the supernovas that we have identified with the naked eye over the last centuries have exploded several thousand light years away and have remained without consequence for our planet. But it has happened in the past that these explosions took place much closer, so close that their effects were not simply visible, but literally terrible. It is believed that 2.6 million years ago, a supernova exploded 30 times closer to us than the one observed in 1006. And this proximity had major consequences. The story always begins the same. A new star appears in the sky. Abnormally bright, it quickly gains in power until it becomes as luminous as the full moon, virtually eclipsing the entire firmament. Soon, it starts to almost turn day into night, and during the day, the star is still there. For a few months in the sky, there is like a second little sun. Except that, this time, the proximity of the dying star, much more pronounced and powerful than the previous ones, is going to wreak havoc. Its light, coming from the depths of space, carries destruction within it. Because, in the wake of its explosion, puffs of high-energy particles were projected in all directions, like so many waves on the surface of a raging cosmic ocean. And after spending more than a century silently traveling through interstellar space at the speed of light, some of the supernova's energy hits our planet in the form of a deluge of gamma radiation and cosmic rays, which will generate, by relentlessly penetrating the upper atmosphere, a rain of secondary energetic particles, triggering a series of planetary-scale upheavals. At a few tens of kilometers altitude, the ozone layer is attacked and a large part of this protective shield is destroyed, leaving the Earth's surface vulnerable to the most aggressive solar radiation and cosmic rays. For all living beings evolving on the surface, the light of our star becomes a threat. On Earth, plants are dying in series, and in the oceans, marine organisms evolving in the layers close to the surface, such as phytoplankton, are doing the same. In the space of a few months, the collapse of the first links in the food chain leads to that of a large part of the biosphere. The supernova adds a general climate upheaval in the wake of this massacre. Because, by hitting the molecules of our atmosphere, cosmic rays have triggered a cascade of chemical reactions and created large amounts of nitrogen oxide, which will gradually form a vast cloud cover, covering the planet with a strange opaque and misty veil. In a few years, the amount of sunlight reaching the ground drops dramatically, and the global temperature does the same. A nuclear winter of planetary scale sets in. As crazy as it may seem, this scenario of a mass extinction and climate upheaval caused by the explosion of a supernova is considered very credible. Because the global cooling is brutal from the beginning of the Pleistocene, which saw the average temperatures of our planet drop by nearly 5 degrees. Begins roughly at the same time when we date the impacts of the most powerful of the last supernovas, clearly identified. Indeed, in the sediments dating from this time, large quantities of a strange element, iron-60, a radioactive isotope of iron, to which, let's be honest, almost no one pays any attention. But if you are a nuclear physicist, it's one of your favorite atoms. Because iron-60 can only come from elsewhere in the cosmos, since it only forms under infernal conditions, reigning at the heart of exploding stars. Its presence in Pacific Ocean sediments, Antarctic ice, and lunar rocks is a testimony, a message engraved in the very fabric of our solar system. The stone, and which tells us that in the past, the Earth was indeed struck by radioactive dust, propelled into space by the explosion of a dying star. And if you add to that the fact that at the time these particles settled, there are 2 points. 6 million years ago, nearly a third of the marine megafauna in the surface layers disappeared, while animals evolving deeper in the oceans were largely spared. As if protected from cosmic rays by the water's thickness, you start asking yourself questions. And then, we also found indirect traces of these past explosions in our galactic neighborhood. Indeed, when we study the amount of matter we find between the stars using our telescopes, we find that, over hundreds of light years around, it is 1,000 times weaker than its average value in the interstellar medium. In fact, our planet is currently evolving in a relatively empty region of space, which we have named the local bubble. It is believed today that this low-density bubble was somehow carved out by the explosion of several supernovas, whose blasts and shock waves would have pushed and blown away much of the interstellar matter it originally contained. Thus, we believe we have identified no less than 3 supernovas that have occurred in our galactic neighborhood over the last 10 million years. And by studying the concentrations of iron-60 found in the sediments, we were able to estimate that the one dating back to 2.6 million years ago must have exploded some 150 light-years from our planet. That's an absolutely staggering distance that the fastest probes we've so far sent into space would take nearly 3 million years to cover. Another way to visualize it is to say that it's 37 times farther than the nearest star to us. The fact that an explosion can leave its imprint on fossils and rocks and influence the climate of a planet located 150 light-years away gives you a small idea of its power. In fact, it is thought that if this supernova had been even 5 times closer, things on Earth would have, let's say, gone very badly. To convince ourselves, let's play a little game. Knowing the colossal amounts of energy released by supernova explosions, we can have fun trying to see from what distance these explosions are relatively harmless and what is the size of their sphere of death. The distance from which they are inevitably fatal. Imagine a supernova exploding a light-year away. In that scenario, all the lights would appear scarlet red. Death would arrive in the wake of a blinding light filling almost the entire sky and eclipsing the sun in an insidious and silent form. That of an uninterrupted flow of gamma rays and extremely energetic cosmic radiations that would pierce like so many invisible arrows. And traveling at the speed of light, absolutely all living beings on the surface of the Earth. In fact, a light-year away from the explosion. Even if we took refuge deep in a nuclear shelter to escape the intensity of the radiation, we would have absolutely no chance of survival. On one hand, because these high-energy cosmic particles would completely peel off the atmosphere, and on the other hand, because we would be within the range of the kinetic energy of the explosion. In other words, large chunks of matter torn from the star would come in the weeks and months following the arrival of the rays, striking our planet at a few % of the speed of light, to the point of melting the surface. Let's take a step back. 5 light-years away from the explosion, which is roughly the distance to the nearest star to us. Currently, it still smells terribly burnt, because the ozone layer would literally be reduced to nothing by the power of radiation. And in just a few hours, Earth would completely lose its natural shield against cosmic and solar radiation. The consequences would be immediate and tragic. The ultraviolet rays from the sun, like those coming from the supernova, would scorch the surface of our planet. Let's go back a little further. even 10 light years away. And although the energy of the explosion would have significantly diluted in space, the consequences would still be catastrophic. As a whole, the atmosphere should be able to withstand the passage of gamma radiation and clusters of atomic particles which, projected at speeds close to that of light, still contain as much energy as a bullet. But even at such distances, after the incredibly intense radiation has passed, the greatest challenge still remains. Because the shock front of the explosion continues its progression through space. And hundreds of years after the sky suddenly lit up? The expanding remnants of the supernova, rich in heavy radioactive elements forged during the explosion, will inevitably end up reaching our planet and deposit there in the form of a rain of atoms, causing long-term lethal genetic mutations. If you doubt the ability of a supernova to eject matter at such a great distance, the Crab Nebula should change your mind. These streams of stellar matter that you're looking at were ejected nearly 1,000 years ago by the explosion of a supernova, that of 1054. And today they spread over 11 light years wide. That's almost 3 times the distance to our nearest star. And a millennium after the star exploded, the shockwave continues to expand into the surrounding space, even being 20 light years away from the explosion. It is believed that 50% of the ozone layer would be completely destroyed, and any form of life evolving on the surface literally wiped off the map. Thus, the explosion of a supernova somewhat draws a virtual bubble, a sphere of death with a minimum diameter of 40 light years around it, and within which the fury of the explosion is simply unbearable for life evolving on the surface. It is believed that it is from 30 to 50 light years away from the epicenter that the power of the star is sufficiently diluted in space, so that we completely exit the sphere of death. Beyond this minimum safety distance, it continues to shake. Atomic nuclei always come in numbers, impacting the Earth at nearly 10,000 kilometers per second, leaving red-hot marks with iron 60. But overall, the radioactive fallout remains bearable, and all the harm indicators have decreased enough so that the costs can be absorbed. So I guess a question is burning your lips. Are we in danger? Are there giant stars around us about to explode and close enough to be able to kill us? Within 1,000 light years radius around Earth, there are 24 stars that will end their life in supernova. And a certain number of them should even explode in the near future. By near future, we mean here a few tens to hundreds of thousands of years. Maybe some have already exploded, and that the burst of light produced by their death is on its way to us. As I speak these words, well, said like that, it sounds pretty bad for us, but don't worry. Betelgeuse, a red supergiant nearing the end of its life, serves as an example. Is the equally massive and threatening Antares, which is about 550 light years away, as distant as 640 light years from Earth? In fact, the closest of these stars likely to turn into a supernova is now 240 light years away from us. In short, all these potentially threatening stars are currently too far away to be anything other than an unparalleled spectacle of matter and light bursting forth. And if one of them exploded today, it would only crudely brand our memories. But don't rejoice too quickly. Already, all these stars are moving in the galaxy, and these incessant movements in the sky can just as well move a potential danger away as bring it closer. It is thus estimated that on average, a star comes within less than a light year of Earth every 500,000 years, from Earth every 500,000 years. And nothing tells us that in the future, the drift of these stars will not end up dangerously bringing one closer at the precise moment when it will explode. And then, above all, we think we have discovered 2 types of giant stars capable of extending the size of the sphere of death in absolutely terrifying proportions. The first of these have the particularity of having spat out into space a large part of their outer layer even before exploding. And hundreds of years after being ejected from the star, when this cocoon of drifting matter is caught up by the ejections coming from the explosion, it becomes terribly radioactive and starts to emit large amounts of rays in all directions, 10 which, for thousands of years, will be able to strip the protective layers of the high atmosphere of a planet located up to 150 light years away. As for the second type of stars that you are likely to dislike, these are hypernovas, a type of supernova on steroids and whose explosion is 10 times more powerful than an ordinary supernova. It has the particularity of concentrating the vast majority of the energy released into two beams of emissions that extend the range of the damage to nearly 10,000 light-years away. In fact, these kinds of death rays, produced by hypernovas and dubbed gamma-ray bursts, have an energy density such that we are able to capture those that come to us from explosions that took place at the edges of the observable universe. Even being located 1,000 light-years away from the hypernova, getting swept by the three beams of a gamma-ray burst is certain death. And up to 10,000 light-years away, it's the assurance of a deep bite into the atmosphere. And I imagine you'll be happy to learn that in our galactic neighborhood there are a number of giant stars capable of creating such cataclysms. Such as the gigantic and already partially torn Eta Carina, which located some 7,500 light-years from Earth, is on a cosmic timescale. In the last moments of its life, or the terribly unstable WR104, whose convulsions and fits of anger foreshadow a cataclysmic end, whose theater takes place about 8,000 light-years away from us, and which could well, at the time of its death, give birth to one of these rays, which can contain more energy than our sun will emit over the entirety of its existence. So much so that it is thought that being in the line of fire of such a beam for just 10 seconds could be enough to destroy a quarter of the ozone layer, and in the process trigger a new mass extinction. Gamma-ray bursts are extremely narrow, and supernovas are so rare that it's estimated a star of this type explodes only once per million years on average. In a galaxy like ours, one might be tempted to think that it would really take bad luck to get hit by one. And the funny thing is, it's entirely possible that in this little game, we've already lost in the past. Because the hypothesis of a gamma-ray burst is seriously considered to partly explain one of the most terrible mass extinctions our planet has known in its long history. The massive extinction of the Upper Ordovician 440 million years ago, during which 440 million years ago, 85% of species disappeared. It is estimated that, statistically, our planet must find itself once every billion years on average, right in the line of fire of one of its beams. That leaves a 1 in 2 chance of getting hit in the next 500 million years. Atmosphere and cold sweat. Anyway, what's the point of worrying? Life began on Earth over 4 billion years ago, and the fact that it's still here should generally reassure us. Each time resilient, it has managed to start over and reinvent itself. Above all, its energetic rays travel nearly at light speed. When the message arrives, it's already too late. Perhaps one day we will look up at the sky and witness the appearance of a new star, fascinated by this light of an unheard-of beauty and violence. Like a rabbit caught in the headlights of a massive truck. We will stay there, motionless, to contemplate, paralyzed by the birth of a second sun, without measuring. That this spectacle is that of the last dance, of a star taking its bow, and that this light is that of death on its way. In the end, each time it's the distance to the point of explosion that will determine whether this bewildering spectacle will or will not be the last thing we see. At the heart of these explosions, there is a kind of relentless logic, that of a universe in perpetual transformation, where destruction is just the other side of creation. Ironically, it is thought that it was the shock wave from a supernova that 4.6 billion years ago initiated the gravitational collapse of the immense cloud of gas and dust that gave birth to our solar system. In this sense, without these explosions, the sun, the earth, and everything on it would not be here. And in doing so, we are indirectly the distant heirs of these abrupt changes, the children of the cosmos, and the death of stars that can reshuffle the deck and overturn the table. 4.6 billion years later, the Australopithecus, our distant ancestors, had to face the upheavals caused by another supernova. Who may have come to change the climatic conditions by forcing species to adapt and evolve. Thus, paradoxically, this cosmic catastrophe may have laid the foundations of our own existence, contributing to the emergence of humanity as we know it. If you want to have fun thinking about the influences that certain stars might have on us, leave astrology and embrace astronomy. I'm pasting the link here to the episode that describes in detail the phenomena behind supernovas. Remember to hit the bell and subscribe. Because in an upcoming episode we will see that these deadly phenomena are also, in a counterintuitive way, absolutely necessary for the emergence of life. Because these giant stars are real cosmic forges, whose explosions scatter into space. Dust and ashes that serve as basic elements to ignite other stars, build planets, and even living beings.